Europa looks silent from a distance, just a frozen moon orbiting Jupiter in the deep cold of space. But beneath that cracked shell, scientists now see growing signs of something astonishing, a vast hidden ocean, strange chemistry, possible plumes, and new clues that life could survive there in ways unlike anything on Earth. If that sounds fascinating, make sure to like the video, subscribe to the channel, and stay with us as we explore why Europa may be one of the strangest and most promising places to search for life beyond Earth. Far from the Sun, in the broad outer reaches of the solar system, Jupiter moves along its immense path with patient regularity. It is a giant world of gas, cloud, storm, and magnetism, so large that the other bodies around it seem arranged in its presence like a smaller system within the greater one. Around this planet travel many moons, each held by Jupiter's gravity and shaped in some degree by its power. Among them is Europa, one of the 4 large moons first seen by Galileo in the early 17th century. These 4, now called the Galilean moons, are Io, Europa, Ganymede, and Callisto. They circle Jupiter in an orderly pattern, each with its own speed, its own distance, and its own history. Europa occupies the second position of these 4 major moons, orbiting between Io, which lies closer to Jupiter, and Ganymede, which travels farther out. At this distance from the Sun, sunlight grows thin. It still reaches Jupiter and its moons, but it arrives weakened, spread across a much larger space than it crosses near Earth. Jupiter receives only a small part of the light and warmth that Earth receives. Even so, the planet remains visually dominant, because it is enormous, bright, and banded, with its reflected light standing out against the dark. For any moon moving around it, Jupiter is not a distant point in the sky. It is a vast presence. Europa circles within that presence, tied not only to the planet's mass but also to the larger environment Jupiter creates around itself. Europa completes one orbit around Jupiter in a little more than 3.5 Earth days. This motion is steady and fast, guided by gravity with precise repetition. Like many moons in the solar system, Europa keeps the same face turned toward the planet as it orbits. This state is called tidal locking, a condition in which the period of rotation matches the period of orbit. As a result, one hemisphere of Europa always faces Jupiter, while the opposite hemisphere always faces outward into space. This does not mean one side remains in constant sunlight and the other in darkness, because the moon still circles the planet and both hemispheres pass through day and night as the system turns beneath the sun. What remains fixed is the direction toward Jupiter. Europa's orbit is not an isolated path. It is part of a gravitational pattern shared with Io and Ganymede. These 3 moons are linked in what scientists call an orbital resonance, a repeated mathematical relationship between their orbital periods. For every orbit completed by Ganymede, Europa completes 2, and Io completes 4. This relationship matters because it keeps Europa's path from becoming perfectly circular. Instead, the orbit remains slightly stretched. That small departure from a perfect circle has important effects on the moon's motion and shape. But here, at this outer level of description, it is enough to note that Europa does not simply drift in a calm, closed circle. It moves under a rhythm maintained by the gravity of neighbouring moons as well as by Jupiter itself. The space around Jupiter is not empty in any simple sense. It is filled with fields, particles, and motion. The planet's gravity reaches far, holding dozens of moons and guiding smaller fragments of rock and dust. Its magnetic field extends outward across an enormous region, enclosing the planet in a vast magnetic domain. Within this region move charged particles, many of them supplied in part by volcanic activity on Io, and then caught and accelerated by Jupiter's rotation and magnetism. Europa travels inside this system, not beyond it. Its orbit lies deep within Jupiter's magnetic influence, and this alone makes the Moon different from a small icy body drifting in the distant solar system without a giant planet nearby. Around Europa, space is active. Seen from far away, Europa is small beside Jupiter, yet it is not a minor object in absolute terms. It is a substantial moon, slightly smaller than Earth's moon, and one of the larger satellites in the solar system. Its nearly spherical shape reflects the pull of its own gravity, strong enough to draw it into a rounded form. Its surface brightness makes it stand out among many other moons. Even telescopic views from Earth show Europa as a bright point moving in careful sequence around Jupiter. Spacecraft images reveal more, but from this broad vantage the essential fact is simple. Europa belongs to a family of large worlds, not to a swarm of irregular fragments. It is a planetary body in miniature, with its own structure and its own long development. The Jupiter system also has a strong sense of scale in time. Light from the Sun takes many minutes to reach Jupiter. Signals sent from spacecraft near Jupiter take long stretches of time to travel back to Earth. The motions of the moons, however, remain dependable enough that their positions can be predicted with great accuracy. For centuries, astronomers have watched these repeated motions and used them to understand gravity, orbital mechanics, and the organization of planetary systems. Europa thus enters science first not as a place of immediate detail, but as part of a grand moving arrangement. It is one member of a system that teaches order through repetition. Yet this order does not imply simplicity. Jupiter is not merely a planet with companions. It is the center of a powerful local environment. Its rotation is rapid, its magnetic field is immense, its influence reaches into the behavior of plasma, dust, radiation, and orbital motion. Europa travels through changing conditions as it moves along its path. At one moment it is on one side of Jupiter relative to the Sun, later it passes to another. It enters and leaves regions shaped by shadow, by particles, and by changing magnetic geometry. Even before attention turns to the Moon's own surface, this broader setting begins to explain why Europa matters. It exists not as an isolated frozen world, but as a moon embedded in one of the most dynamic planetary systems in the solar system. Modern interest in Europa grows from this setting as much as from the Moon itself. Observations from telescopes, from the Galileo mission in the 1990s, from the Hubble Space Telescope, and now from the continuing work surrounding Europa Clipper and ESA's JUICE mission, all place Europa within the larger Jovian context. NASA describes Europa as one of the best places beyond Earth to look for environments where life could exist, but that judgment begins with position. Europa circles a giant planet in a region where gravity and motion continually interact. It belongs to a system rich in energy, rich in structure, and rich in scientific consequence. Before any closer examination, Europa first appears as a bright moon moving in the cold outer domain of Jupiter, held in a precise orbit, suspended within a vast field of planetary power. Around Jupiter, sunlight arrives in a weakened stream. By the time it crosses the long distance from the Sun to the Jovian system, it has spread thin across a vast sphere of space. What falls on Europa is still true sunlight, still the same radiation that lights Earth, but its force is much reduced. The Moon receives only a small fraction of the solar energy that reaches the inner planets. In this outer setting, brightness no longer brings warmth in the familiar way. Light remains present, yet cold governs the surface. Europa turns through day and night as it travels round Jupiter, though it always keeps the same face toward the planet. The sun rises and sets over the icy plain in a slow rhythm linked to the moon's orbit. A Europan day, measured from one sunrise to the next, lasts about as long as its orbital period around Jupiter, a little more than 3.5 Earth days. The passage of light across the surface is therefore unhurried. Dawn does not rush. It advances gradually over frozen ground, over ridges and plains of ice, over fractures that catch light at low angles and then lose it again. Noon does not blaze with the sharp strength known on Earth. It brings a pale illumination, enough to define the terrain clearly, but not enough to overcome the deep chill that has settled there for immense spans of time. In this faint sunlight, Europa's surface reflects strongly. The moon is one of the brightest objects in the solar system because its exterior is made largely of water ice, which returns much of the light that reaches it. This brightness is important. A dark surface would absorb more solar energy and warm slightly more. Europa's pale shell does the opposite. It sends much of the incoming light back into space. The result is a surface that remains extremely cold even under direct illumination. Sunlight sketches the landforms, but it does little to soften them. Temperatures across Europa's surface are usually described as far below the freezing point of water, and far below the conditions in which liquid water can remain stable in the open. Near the equator, where sunlight strikes more directly over time, daytime temperatures may rise to around -160 degrees Celsius. In colder regions and during darkness, temperatures can fall closer to -220 degrees Celsius. These values vary with location, surface texture, and time of day, but the general truth is steady. Europa's exterior belongs to a severe cold. It is a domain where ice behaves not as a seasonal covering but as rock-like material, hard and durable under the low temperatures that dominate the surface. This deep cold shapes everything visible. The uppermost ice is brittle in many places. It preserves fractures, ridges, and broken zones over long periods because ordinary melting does not erase them. Any frost that forms and settles does so under conditions of near vacuum and extreme chill. The boundary between light and darkness matters, but not in the gentle way it matters on Earth. On Europa, day does not invite flowing water, rain, or thaw. It alters the surface only slightly, shifting temperature by degrees across a range that remains bitterly cold from beginning to end. Jupiter also plays a visual role in Europa's cycle of light. In the Europan sky, Jupiter would appear immense, far larger than Earth's moon appears from Earth. It would dominate one part of the sky, nearly fixed in place because of tidal locking. Its cloud bands, storms, and changing colours would present a great disk above the horizon, though often softened by distance and lighting conditions. The brightness of Jupiter contributes reflected light at times, but this is not a major source of heat. It is a spectacle of scale rather than warmth. Europa remains cold beneath it. At intervals, Europa passes into Jupiter's shadow. During these eclipses, direct sunlight is cut off altogether. The moon then moves through a darkness created not by its own rotation, but by the giant planet blocking the sun. In such moments, the already weak contribution of sunlight disappears, and the surface is left to radiate heat away into space. Because the surface begins so cold, these shadow passages do not transform the environment in dramatic visible ways, yet they belong to the thermal rhythm of the moon. Europa does not simply alternate between pale day and pale night. It also endures regular plunges into a deeper darkness cast by Jupiter itself. The low gravity of Europa and the near absence of any substantial atmosphere also affect how light and cold are experienced at the surface. Earth's atmosphere scatters sunlight, softens shadows, carries heat, and supports clouds and weather. Europa has no thick blanket of gas to do any of these things. Its atmosphere is only an extremely thin veil, so slight that it cannot distribute warmth or create weather in the terrestrial sense. Light falls more directly, shadows remain stark. Heat gained from sunlight is not held by air or circulated by wind. The surface gives up energy readily. Cold therefore persists with little resistance. In such conditions, the landscape is governed by contrast rather than comfort. Bright ice lies under a dark sky. The sun appears smaller than it does from Earth, though still strong enough to define direction and cast long shadows. Illumination can be clear while warmth is absent. This combination gives Europa its outer calm. Nothing in the faint daylight suggests a welcoming surface. It is beautiful in a restrained and distant way, a frozen brightness under a black sky, shaped by cold more than by light. The importance of this outer thermal regime is not that it explains all of Europa, but that it sets the terms of the visible exterior. The moon's surface is locked in an environment where sunlight is real yet weak, where reflection is high, and where temperature remains intensely low across both day and night. This does not mean the entire moon is equally cold in all places or at all depths. It means that the outermost skin, the level exposed directly to space, exists under severe thermal limits. Here the ice endures. Here light reveals without warming. Here the first impression of Europa remains simple and exact, a bright, frozen world under thin sunlight, turning slowly through long days in the far cold beyond the inner solar system. Around Europa, space is not calm. It is filled with invisible motion, and much of that motion carries force. Jupiter possesses an immense magnetic field, one of the largest structures created by any planet in the solar system. This field extends far into surrounding space and traps charged particles within it, electrons and ions, which are atoms or fragments of atoms carrying electric charge, move through this magnetic domain in great numbers. They do not drift softly, they are accelerated, redirected, and swept along by the combined action of the magnetism and Jupiter's rapid rotation. Europa circles deep inside this restless environment. Radiation, in this setting, means energetic particles and electromagnetic effects capable of altering matter. Around Jupiter, the most important radiation hazard near Europa comes from charged particles trapped in the planet's magnetosphere. A magnetosphere is the region around a body where magnetic forces control the motion of charged particles. Jupiter's magnetosphere is vast and powerful. It reaches far beyond the orbit of Europa and contains belts and zones of energetic particles far stronger than those surrounding Earth. These particles strike Europa continually. They arrive from the space around the Moon rather than from any atmosphere above it, because Europa has almost no atmosphere to provide meaningful protection. The source of this hostile environment lies partly in Jupiter itself and partly in the wider Moon system. Jupiter rotates in less than 10 Earth hours, an extremely fast spin for so large a planet. Its magnetic field turns with it, sweeping charged material around at high speed. One important contributor to that material is Io, the innermost Galilean moon, whose intense volcanism releases large amounts of sulfur and oxygen into space. Some of this matter becomes ionized, meaning electrons are stripped away and the particles gain electric charge. Once charged, They can be trapped by Jupiter's magnetic field and carried through the system. Europa moves through this circulating flow. It does not sit outside it as a distant observer. It is immersed in it. As Europa orbits Jupiter, charged particles stream past and bombard its exposed exterior. Electrons strike the surface ice. Heavier ions do as well, though their behavior differs because of their greater mass. This bombardment penetrates only the uppermost part of the surface, but there it is relentless. Molecules are broken apart, chemical bonds are disturbed, atoms are displaced. The top layer of ice is gradually altered by repeated irradiation. The surface that appears so still in images is, at the microscopic scale, under constant assault from the surrounding space environment. This radiation does not mean the moon glows with visible violence. The process is mostly silent and unseen. No storm clouds gather, no flames move over the ice, yet energy is continually being delivered into the outermost material. Water molecules at the surface can be split into hydrogen and oxygen-bearing fragments. Other compounds mixed with the ice can also be changed. Over time, this leads to the production of new chemical species, some of them highly reactive. The surface becomes not only frozen but chemically processed by radiation. The topmost grains and crystals record the influence of Jupiter's magnetosphere in their composition. The distribution of radiation across Europa is not perfectly even, because the moon moves through Jupiter's magnetic field while keeping one face toward the planet. Different regions of the surface receive different patterns of bombardment. The trailing hemisphere, the side that faces backward relative to Europa's direction of motion around Jupiter, tends to receive stronger particle impacts, in a simple sense. This hemisphere moves into the oncoming flow of energetic material in a way that exposes it more directly. The leading hemisphere, facing forward along the orbit, experiences a different balance. These differences help shape large-scale surface chemistry and color variation. Even from afar, the moon's two hemispheres do not tell exactly the same story. The importance of this radiation environment becomes clearer when compared with Earth. On Earth, a thick atmosphere and a protective magnetic field shield the surface from much of the charged particle flux arriving from space. At Europa, neither defense exists in any strong form. Its atmosphere is far too thin to protect the surface, and the moon does not possess a global magnetic shield strong enough to stand off Jupiter's trapped particles in the way Earth's field stands off much of the solar wind. The result is an exposed ice shell under a continuous rain of energetic particles. For any spacecraft operating near Europa, radiation is a serious engineering challenge. For the moon's uppermost materials, it is a shaping force. Yet the effects of radiation are not only destructive, they also create chemical possibilities. When radiation breaks apart water ice and salts or other compounds present near the surface, it can produce oxidants, substances that are chemically eager to accept electrons in later reactions. On Earth, oxidants can support important forms of metabolism and broader chemical cycles. At Europa's surface, these oxidants are produced under severe and lifeless conditions, but their presence matters because they represent stored chemical energy. At this outer level, it is enough to see that radiation does more than scar the surface. It transforms it chemically, creating ingredients that may become important if they are moved elsewhere. Still, the surface itself remains a difficult place for life as it is understood on Earth. The radiation levels near the exterior are intense enough to damage complex organic molecules and to make long-term survival at the immediate surface extremely challenging. The topmost ice is therefore not treated by scientists as the most likely place for living systems to persist. The outer shell is instead a zone of exposure, where the environment of space meets frozen water directly and without mercy. It is a boundary region, open to bombardment and alteration. From a distance, Europa may seem quiet, bright, and still beneath the black sky, but the space around it is active in an unceasing way. Jupiter's magnetic power sweeps particles across the Moon's orbit. The ice receives their impact day after day, orbit after orbit, over spans of time so long that the process becomes part of the Moon's identity. Here at the outer edge of Europa's story, before the eye settles on cracks or ridges or chemical stains, the first deeper truth emerges. The Moon is wrapped not in air, but in radiation. Its surface stands inside a powerful invisible weather of charged particles, shaped by a giant planet whose influence reaches into every exposed crystal of ice. Europa presents a face of ice. From a distance, it appears bright, pale, and almost simple, yet closer views show a surface marked everywhere by structure. It is one of the smoothest large solid surfaces known in the solar system. Not because nothing has happened there, but because the outer shell is made of water ice and has been shaped in ways very different from the rough stone landscapes of many rocky worlds. NASA descriptions of Europa repeatedly emphasize the same visual truth. The Moon is crisscrossed by ridges, fractures, and bands, with relatively few large impact craters and with broad areas that remain low and even rather than mountainous. The eye does not meet towering peaks or deep crowded basins. It meets ice marked by lines. The brightness of Europa is the first striking feature. Much of the surface reflects sunlight strongly because much of it is made of water ice. In natural colour views, the Moon appears white to faintly bluish in many places, though this is not the uniform white of fresh snow on Earth. It is a colder and subtler brightness, broken by stains, streaks, and long dark markings. Some regions look cleaner and more reflective, while others carry reddish, brownish, or rust-coloured tones. These colour differences are not random decoration. They trace the structure of the surface. The darkest material often follows cracks, bands, and disrupted regions, so that the Moon seems written over by long lines of altered ice and mixed material. Those lines dominate the visible landscape. They run across the plains in pairs, clusters, and networks. Some are narrow, some broad, some nearly straight over long distances, and some gently curve. Many are ridges, which are raised linear features standing above the surrounding surface. A ridge is a long, narrow elevation, like an extended frozen seam. On Europa, ridges often occur in double form, with a central trough or groove between two parallel raised flanks. These double ridges are among the most characteristic landforms on the Moon. They may extend for many kilometers, crossing older markings and being crossed in turn by younger ones, so that the surface resembles a layered record of repeated cracking and rebuilding. Between and around the ridges lie fractures, which are breaks in the ice shell. In visible images, fractures appear as dark or shadowed lines, sometimes crisp and narrow, sometimes broader and more complex. Some remain simple cuts through the ice. Others widen into bands, where the separation between the edges becomes large enough to create a distinct strip of different texture or colour. NASA descriptions of Europa's bands often note that they are places where the surface seems to have spread apart in the past. In visual terms, they look like long scar-like zones, darker than the surrounding plains, often bordered by ridges and lined with repeated internal markings. They give the Moon a woven appearance, as if the surface has been pulled, parted, and marked over again. The planes between these lineaments are not featureless, though at low resolution they can seem calm. Closer inspection shows subtle textures, low rises, small pits, and countless intersecting markings. Even where a region looks open and comparatively smooth, its smoothness is relative. Europa lacks the heavy crater saturation seen on many ancient surfaces, but it does not lack detail. The ice carries fine structure almost everywhere. Light striking at a low angle reveals relief that disappears under more direct illumination. Small ridges cast narrow shadows. Grooves catch darkness. Faint hummocks and shallow depressions emerge and then fade again as viewing geometry changes. The moon's surface is therefore not only patterned but delicate, full of low forms visible only when light falls in the right way. Impact craters are present, but they are uncommon compared with many other worlds. This scarcity is visually important. On a heavily cratered body, circles dominate. On Europa, lines dominate. The eye follows length rather than roundness. Where craters do appear, they often seem subdued, softened, or altered relative to the sharp classic bowl forms seen on drier rocky bodies. The broad absence of large ancient crater fields contributes to the impression that Europa's visible exterior has not stood unchanged for the age of the solar system. Even without entering deeper interpretation, the eye can see that this is not a static museum of impacts. It is an icy exterior where linear features have greater authority than collision scars. Another visible aspect of Europa is the contrast between order and disruption. Some areas are covered with long, coherent ridges and parallel structures that give a sense of directional pattern. Other areas appear broken into irregular pieces. In these disturbed regions, blocks and plates of surface material seem jumbled, rotated, or separated by darker matrix. NASA and other mission descriptions refer to many such disrupted places as chaos terrain. In purely visual terms, these regions interrupt the long disciplined line work of the ridge plains. They look rougher, patchier, more confused. Edges of broken pieces stand out. Shapes do not align as neatly. The eye moves differently across them, less along continuous lines and more among scattered fragments. This variety prevents Europa's face from becoming monotonous. The moon is unified by ice, yet diverse in texture. Color deepens that diversity. Enhanced color images, while not matching natural human vision exactly, help show differences in composition and freshness across the surface. Relatively pure water ice often appears brighter and bluer or whiter, while regions richer in non-ice material tend toward reddish or brownish tones. Even in more natural views, the reddish markings remain notable. They collect along fractured bands, as if material has gathered or been altered there. These colours give Europa's face its strange restraint. It is not vivid in the way of a volcanic world. It is pale, marked, and lightly stained, with colour used sparingly by the landscape itself. Large cliffs and tall mountains are not defining features here. Europa's relief is generally low compared with many solid worlds. The surface stretches outward in broad icy expanses, interrupted by linear rises and shallow troughs, rather than by dramatic vertical walls. This low relief adds to the moon's quiet appearance. The terrain appears open. Horizon lines would be long. The land would not close in around an observer with steep enclosing forms. Instead, the surface would unfold as a cold plain of intersecting ridges, faint colour bands, and smooth reaches of bright ice under a black sky. Taken together, these visible features create one of the most distinctive surfaces in the solar system. Europa is bright, smooth in the large sense, intricately marked in the small sense, and dominated by long dark lines that trace across its frozen shell. Spacecraft images from Voyager, Galileo, and Juno show again and again that the moon's exterior is not blank ice but patterned ice, not simple white but white crossed with rust-coloured seams, not rough with mountains but restless with ridges and fractures. Without moving beneath the surface or ahead into hidden layers, the visible face alone is enough to establish Europa as a world of frozen complexity, where the outer shell carries its history in lines, stains, and broken planes of light. Europa's surface does not look ancient in the way many worlds do. Across much of the solar system, age announces itself through impacts. Old terrain collects craters over immense spans of time, and if little later change occurs, those marks remain. On Europa, that expected record is thin. There are impact craters, but there are far fewer than on many other moons of comparable size. This visible scarcity leads to one of the central conclusions in Europa science. The surface that can be seen today is geologically young. In planetary science, a young surface does not mean recently formed in the human sense. It means that the visible exterior has been renewed, reshaped, or replaced often enough that older scars have not accumulated in large numbers. The face of Europa has not remained fixed for the age of the solar system. It has changed. This youth appears not only in the low crater count, but in the condition of the terrain itself. The ridges, bands, and broken zones described across Europa do not sit on a dead shell. They suggest motion, not rapid motion in the everyday sense, and not motion that can be watched directly from one hour to the next, but motion spread across long periods. The ice crust behaves as a material under stress. It fractures, shifts, opens, and in some places seems to separate and receive new material between older parts. The visible surface, therefore, gives the impression of slow restlessness, as if the moon's frozen exterior has been worked over repeatedly by forces acting from within and through orbit. Many of Europa's broad bands are especially important in this regard. A band is more than a simple crack. It is a region where the surface appears to have pulled apart and been modified as the separation developed. Scientists compare some European bands, in a limited way, to the spreading centers of Earth's sea floor, not because the processes are identical, but because both involve extension, the pulling apart of a surface, on Europa. Some matching patterns on opposite sides of a band seem to fit together when reconstructed, as if the terrain was once joined and later separated. This kind of geometric evidence is one of the strongest visual signs that the crust has moved. The moon's surface can sometimes be read like a broken sheet whose pieces still remember how they once aligned. The same sense of motion appears in displaced blocks and shifted lanes of terrain. In some places, long lines crossing the surface are interrupted and offset, with one section no longer meeting the continuation directly across a fracture. The simplest reading is that one side moved relative to the other. These offsets are not random visual accidents. They are part of a pattern seen in many regions of Europa. The crust seems to have cracked and then adjusted, leaving a record of strain. Even where the displacement is modest, the meaning is clear. The shell is not merely marked, it has responded mechanically to stress. That stress is closely tied to Europa's orbit around Jupiter. Because the orbit is kept slightly non-circular by gravitational resonance with Io and Ganymede, Europa experiences changing tidal forces as it moves. A tide, in this scientific sense, is a deformation caused by gravity. On Earth, tides are most familiar in the rise and fall of oceans. On Europa, the whole moon flexes. Jupiter's pull changes slightly over the course of each orbit, and the moon's shape adjusts in response. This repeated flexing generates internal stress in the ice shell, The crust is bent, stretched, and compressed in patterns that vary with place and time. Over long intervals, those repeated stresses can fracture the ice and help drive large-scale rearrangement of the outer layers. The visible terrain preserves the results of these cycles. Long ridges may form where fractures open and close repeatedly, squeezing material upward or reorganizing near-surface ice. Broad bands may mark places where the crust separated more substantially. Networks of intersecting cracks suggest that the direction or intensity of stress changed over time. One generation of features crosses another, showing that the surface did not change in a single event. It changed in episodes. Europa's young appearance is therefore not the product of one renewal, but of many. The crust has a history of repeated activity recorded in overlapping structures. In some regions, the signs of movement become more dramatic. Large blocks of older surface seem to have broken free, rotated and shifted from their original positions. Their margins no longer align cleanly with neighbouring ground. Darker material fills the spaces between them, or rougher textures interrupt the former continuity. These landscapes suggest that portions of the outer shell have been mobilized, at least locally. The movement may not be simple sliding across a flat plane. It may involve braking, slight drifting, tilting, or partial sinking within softer or warmer material below. But from the visible surface alone, the essential point remains that pieces once belonging to a more continuous crust no longer sit where they began. Some researchers have gone further and identified evidence consistent with forms of ice tectonics that resemble, in broad principle, plate tectonics on Earth. Plate tectonics on Earth refers to the movement of rigid outer plates over a deeper, warmer layer, leading to spreading, collision, and recycling. Europa is not Earth, and its shell is ice rather than rock. Still, certain parts of the Europan surface appear to record both the creation of new surface and the disappearance of older surface. In some areas, evidence has been interpreted as showing that a cold, brittle slab of ice may have been forced downward into warmer surrounding ice. This interpretation remains more specific than the broader conclusion of crustal motion, but it fits the larger picture of an outer shell that is not static. The visible terrain allows the possibility that parts of Europa's crust have not only spread apart but also been recycled. The youth of the surface also depends on time. A terrain can look young because it formed recently, or because it has been renewed often. Europa likely reflects the second condition over wide areas. Its crust appears to have been repeatedly reworked by fracture, extension, displacement, and resurfacing. Old marks are erased not by wind or rain, not by rivers or vegetation, but by the moon's own icy activity. The frozen shell changes enough to overwrite itself. What remains visible is therefore only the latest readable layer of a much longer story. Seen in this way, Europa's surface is neither still nor chaotic in the simple sense. It is organized by stress and altered by motion. Lines offset, bands widen, blocks shift, and older surfaces yield to newer ones. The crust behaves like a shell under continual gravitational working, strong enough to fracture, weak enough to move, and active enough to remain young in appearance, even before any attention turns to heat deeper down or to the unseen ocean below. The outer ice already tells a careful truth. Europa's face is young because it has not stopped changing. Its frozen crust moves slowly through planetary time, and the terrain visible today is the latest arrangement left behind by that motion. Across Europa's bright crust, some of the most revealing features are not the longest ridges or the broadest bands, but smaller landforms that interrupt the surrounding ice with subtle changes in shape. These include pits, domes, spots, and rough patches, each one modest in scale compared with the great linear structures that cross the Moon, yet important because they suggest that the upper part of the ice shell is not uniform and cold in exactly the same way everywhere. In these places, the surface seems to have responded to local changes below it. Something within the near-surface ice has altered temperature, strength, texture, or buoyancy enough to deform the ground above. The result is a landscape where stillness is broken by signs of shallow disturbance. A pit is a depression, a place where the surface sinks below the surrounding plain. On Europa, pits are not simply impact craters in miniature. Many lack the raised rims and ejecta patterns expected from objects striking from above. Instead, they appear more like places where surface material has settled downward, or where part of the near-surface structure has been removed or softened. Some occur alone, others cluster in groups. Their edges may be rounded rather than sharply broken, and their form suggests collapse, subsidence, or local melting and refreezing rather than violent excavation by impact. In a world where open liquid water cannot remain stable at the surface, such depressions point toward changes taking place within the shallow ice, not above it. Domes show the opposite effect. Instead of sinking, the surface rises in low, broad swells. A dome is an upward bulge, a smooth uplift of the crust. On Europa, these domes are often gentle rather than steep. They do not resemble volcanic cones or jagged mountains. They lift the surface quietly, as if a force beneath has pressed upward and then stopped before rupture. In some cases, the uplift may come from warmer ice rising because it is less dense or more mobile than the colder, brittle material above it. In other cases, it may reflect the freezing of material within shallow pockets, where expansion or structural change pushes the overlying crust upward. The exact process is not always certain for any single dome, but the general implication is consistent. The upper ice shell has local zones of internal change. Some Europan features combine both uplift and collapse. A region may show a central depression surrounded by a raised margin, or a dome-like structure broken by later sinking. These mixed forms are especially suggestive because they imply that the near-surface ice does not change in one simple direction. It may warm, soften, rise, partially melt, drain, refreeze, weaken, or collapse in sequence. The visible landform becomes the final expression of several stages rather than one. This complexity matters. It suggests that the shallow crust behaves like an active material layer, capable of evolving locally in response to small differences in heat or composition. Scientists often connect such features with what are called lenticulae. This term refers to small dark spots, domes, pits, and related forms scattered across parts of Europa's surface. The word comes from a shape like a lens, broad and rounded. These landforms are typically much smaller than the great bands and ridges, but they are widespread enough to indicate a recurring process. They seem to represent places where a local anomaly within the ice shell affects the surface. That anomaly may be a pocket of warmer ice, a diapir-like upwelling, or a zone where briny material has interacted with surrounding ice. A diapir is a mass of relatively buoyant material that rises through denser material above it. On Earth, hot rock salt or warm mantle material can behave in this way. On Europa, the comparison is made more carefully and with ice rather than rock, but the idea is similar. Something slightly warmer or more mobile may rise toward the surface and deform it from below. The importance of warmth here must be stated with restraint. Europa's surface remains extremely cold. Even in these altered places, the visible land is still part of a frozen exterior. The suggestion is not that open lakes sit directly under a thin crust everywhere these features appear. Rather, It is that small temperature differences within the upper shell can have major structural consequences over long periods. Ice near its melting point behaves very differently from deeply cold ice. It can flow more readily, deform more easily, and respond to stress in ways that colder, brittle ice cannot. A modest increase in heat, if sustained locally, may therefore be enough to raise a dome, create a pit, or produce a patch of disrupted terrain. Rough patches on Europa add to this picture. In some places, the surface loses the cleaner geometry of surrounding ridged plains and becomes knobbly, mottled, or irregular. These areas may contain small blocks, hummocks, shallow depressions, or uneven textures that suggest local disturbance of the original crust. They are not as extensive as the larger chaos terrains, but they appear to belong to the same family of ideas. The ice has been disturbed from below or within, and the surface records the result. Because these rough patches often occur beside or among domes and pits, they help support the view that Europa's upper shell contains zones of shallow complexity. One proposed explanation for many of these features involves the movement of brines. A brine is very salty water, and salt lowers the freezing point of water. If pockets of briny liquid or slushy ice exist within the shell, they could remain mobile at temperatures where pure water would be solid. Such material might migrate upward short distances, intrude into fractures, or collect in shallow reservoirs. Over time it could weaken surrounding ice, promote deformation, and help produce surface expressions such as spots, domes, or pits. This interpretation is attractive because it links landforms with Europa's broader chemical story, but the details remain uncertain. Observations indicate local disturbance and probably local warmth. Whether any given feature requires shallow liquid, warm convecting ice, rising briny slush, or several processes together is still being worked out. Another explanation focuses on convection in the ice. Convection is the movement of material caused by differences in temperature and density. Warm material rises, cool material sinks, and slow overturn can occur. In Europa's shell, if a layer of warmer, softer ice lies below a colder, brittle lid, slow convection could create upwellings and downwellings that deform the surface above. A rising cell might produce a dome or a dark spot. A sinking cell might contribute to local collapse or a pit. This model fits the broad idea of an ice shell that is active at shallow to moderate depths, though it depends on the exact thickness and thermal state of the shell, both of which remain under study. What matters at the visible level is the pattern these features create. Europa's near-surface crust is not just a cracked frozen roof. It contains places where local conditions have changed enough to warp the surface into bulges, hollows, and irregular patches. The landforms are smaller and quieter than the great bands stretching across the moon, but they may be closer in spirit to the hidden processes beneath. They feel intimate, local, and revealing. A broad ridge announces stress over long distances. A pit or dome suggests that the shallow ice itself has been modified from within. Thus the uppermost shell of Europa becomes more than a brittle crust exposed to cold and radiation. It appears layered, varied, and locally responsive to heat, salt, and movement beneath the surface. Pits sink where support has changed. Domes rise where material presses upward. Rough patches mark places where orderly plains give way to disturbed ground. None of these features alone proves the exact state of the shallow interior. Together, they indicate that Europa's exterior is underlain by a near-surface world of subtle instability, where small differences in warmth and chemistry may reshape the frozen skin from below. Europa's surface is made mostly of water ice, but it is not made of water ice alone. Across the pale crust lie traces of other materials, mixed into the frozen shell or spread along fractures and disrupted regions. These substances matter because they turn a white world into a chemically interesting one. They also matter because the surface is the part that spacecraft can observe most easily. Light reflected from Europa carries clues about what is frozen there. By studying the way different wavelengths of light are absorbed and reflected, scientists can identify broad classes of material and sometimes particular compounds. This work does not provide complete certainty in every case, yet it has steadily shown that Europa's surface includes more than pure ice. The most widely discussed non-ice materials on Europa are salts. A salt, in simple terms, is a mineral compound that can dissolve in water and later remain behind when the water freezes or evaporates. On Earth, familiar salts include sodium chloride and magnesium sulfate, but in planetary science the word covers a wider family of compounds. Observations of Europa over many years have pointed to salt-bearing material on the surface, especially in darker regions associated with fractures, bands, and areas of disruption. These are places where the clean brightness of water ice gives way to stained or altered material. The distribution itself is suggestive. The salts do not appear to be scattered at random. They are often concentrated where the crust has been broken or reworked. This pattern has led scientists to ask where the salts come from. One possibility is that they are connected to the hidden ocean below. If liquid water exists beneath the ice shell and has been in contact with rock for long periods, dissolved minerals should be present in that water. Material moving upward through cracks, shallow reservoirs, or disrupted terrain could then carry some of those minerals toward the surface. Another possibility is that at least some surface salts are produced or modified in place by irradiation and chemical reactions involving pre-existing compounds in the ice. These explanations are not mutually exclusive. Europa's surface likely records both internal transport and external processing. One important advance came from observations suggesting the presence of sodium chloride in parts of Europa's surface. Sodium chloride is ordinary table salt on Earth, though under European conditions it behaves and appears differently. Laboratory work showed that when sodium chloride is exposed to the cold and radiation conditions expected on Europa, it can develop color changes matching some of the yellowish or brownish features seen on the Moon. This result was important because earlier interpretations had often favored sulfate salts, especially magnesium sulfate. The newer evidence did not remove all uncertainty, but it strengthened the case that chloride salts may be significant at Europa, and that the ocean beneath the ice, if it supplies these materials, may be chemically different from some earlier models. The distinction matters because different salts imply different geochemical histories. Sulfate-rich chemistry suggests one type of interaction between water, rock, and oxidized compounds. Chloride-rich chemistry suggests another. In broad terms, chloride salts may point toward an ocean whose composition is in some respects closer to that of Earth's seawater than previously assumed. Though no direct one-to-one comparison should be made too quickly, Europa is its own world, under its own pressures, temperatures, and radiation regime. The value of the salt detections lies not in making Europa familiar, but in narrowing the range of plausible chemical environments. Carbon-bearing compounds have also become a major part of Europa's surface story. Observations with the James Webb Space Telescope identified carbon dioxide in a specific region of the Moon's surface, especially within an area of disrupted terrain known as Terra Regio. Carbon dioxide is simple, but it is important. Carbon is a basic element of life as it is known on Earth, and for a long time scientists could not say with confidence whether Europa's ocean system had access to it in meaningful amounts. The Webb observations strengthen the case that carbon-bearing material is indeed present and, Importantly, that at least some of it likely comes from the Moon's interior rather than arriving entirely from impacts. The reasoning rests on both the location of the carbon dioxide and its geological context. It appears concentrated in a region where material from below may have reached the surface, and it exists on a surface where radiation tends to destroy or alter exposed compounds over time. That means the detected material is probably not ancient residue left unchanged for billions of years. It likely reflects more recent emplacement. This does not mean the surface is rich in complex organic chemistry in the way some popular language may imply. An organic compound is a carbon-based molecule, but not every carbon-bearing substance is equally informative about life. Carbon dioxide is chemically important, yet it is also simple and can arise through non-biological processes. Still, its presence on Europa helps support a broader conclusion. The Moon possesses at least some of the elemental ingredients needed for life, and those ingredients may not be confined to the deep unseen interior. Some are detectable in surface materials that appear linked to internal activity. The question of organics on Europa remains more open. Scientists expect that organic molecules should exist there at some level. They may have been incorporated into Europa during formation, delivered later by comets and asteroids, or generated through chemistry involving carbon, water, and energy sources. Yet direct identification of specific complex organics on the surface remains limited and uncertain. The problem is not only whether such molecules are present, but whether they can survive. Europa's surface is continually bombarded by radiation from Jupiter's magnetosphere. That radiation breaks chemical bonds, modifies molecules, and can destroy fragile compounds over time. Any organics exposed at the surface are therefore under constant attack. Their survival depends on how recently they arrived, how deeply they are buried, what they are mixed with, and how often fresh material is supplied. Radiation also creates new chemistry. When energetic particles strike water ice, salts, and carbon-bearing substances, they drive reactions that would not proceed in the same way in a quiet environment. Molecules are split, recombined, and transformed. This process, often called radiolysis, alters the topmost surface continuously. On Europa, it can generate oxidants and other reactive species that become part of the Moon's chemical inventory. It can also complicate interpretation. A material seen at the surface may not exactly match what was delivered there from below, because radiation may have changed it after exposure. In this sense, Europa's surface chemistry is not a static sample tray. It is an active chemical laboratory under cold and bombardment. The location of chemically interesting materials is as important as their identity. Non-ice substances often cluster in regions where the crust has been disturbed, where bands widen, where chaos terrain appears, or where younger-looking material is exposed. This association suggests exchange between the surface and deeper layers, though the exact pathways remain under study. Some material may rise from the ocean or from pockets within the ice shell. Some may be excavated or redistributed by impacts. Some may form directly at the surface through irradiation. The strongest current view is not that one process explains everything, but that Europa's chemistry is the result of several linked pathways acting over time. For this reason, future missions place great emphasis on chemical mapping. Europa Clipper is designed in part to examine the composition of the surface in much greater detail, to detect salts, gases, dust grains, and possible organic molecules, and to relate chemistry to geology. ESA's JUICE mission will also study Europa during flybys, adding further information about surface composition and active regions. These missions matter because current evidence already shows that Europa's crust is chemically richer than plain water ice. Yet the balance between salts, carbon-bearing compounds, radiation products, and possible organics is still not fully resolved. Thus the surface of Europa becomes more than a frozen shell marked by cracks. It becomes a chemically altered boundary where ice, salt, carbon, and radiation meet. The salts hint at hidden water that has touched rock. The carbon dioxide hints at ingredients rising from below or being preserved in recently exposed terrain. Possible organics remain uncertain in detail, but plausible in principle. And over all of this, Jupiter's radiation keeps working, modifying what lies in the open. Europa's surface chemistry is therefore both a message and a mask. It reveals that important ingredients are present, yet it also changes them as soon as they arrive. Above Europa's frozen surface, space appears empty. There are no thick clouds, no weather systems, no moving sky in the familiar sense. The Moon has only an extremely thin atmosphere, so slight that it would scarcely count as air by Earth standards. Yet within this near vacuum, scientists have found signs that material may at times rise from the surface and briefly enter space. These possible outbursts are often called plumes. A plume, in this setting, is a narrow release of water vapor or icy material from below the surface into the space above. The idea is simple, but the evidence is difficult. Europa does not display permanent towering jets that can be seen in every observation. Instead, the signs are intermittent, indirect, and still under study. This is why the plumes are described carefully as possible or probable, rather than certain in every detail. Interest in Europa's plumes grew from observations made with the Hubble Space Telescope. In ultraviolet measurements, Hubble recorded features near the Moon's limb, the apparent edge of the disk, as Europa passed in front of Jupiter. In a small number of these observations, the data suggested material extending above the surface, consistent with water vapor rising to great height. The detections were not repeated in every observation, and that inconsistency became part of the story from the beginning. If the features are real plumes, they do not erupt continuously. They appear to flare up only at certain times or under certain conditions, and then disappear again. This intermittent character is important. A steady source would be easier to confirm. A sporadic one demands caution. Scientists must ask whether a signal seen once, or a few times, is truly a plume, or whether it might arise from instrumental limits, geometry, or temporary surface and atmospheric effects that do not require an active vent. Over the years, additional studies have strengthened the case that at least some of the detected features are genuine. Repeated signals have appeared in roughly the same region, and some have been associated with areas of unusual surface interest. Yet the evidence remains a case built from multiple suggestive pieces rather than from one simple direct image of an erupting fountain in full clarity. One reason the plume idea matters so much is that it offers a possible connection between the hidden interior and the open space above the Moon. If water vapor is escaping from vents or fractures, then material from within Europa may be reaching the surface and even the space above it without the need to drill through the ice. That possibility has strong scientific value. A spacecraft passing through such a plume could potentially sample material from within the Moon directly, measuring its composition and looking for salts, gases, and complex molecules. This is one reason plume evidence receives such close attention. Even a brief intermittent vent could provide access to information otherwise buried beneath many kilometers of ice. Still, the source of any plume remains uncertain. One possibility is that the vapor comes from the deep ocean beneath Europa's icy shell. In that case, Fractures might open pathways through which water rises, flashes into vapor, and escapes upward. Another possibility is that the source lies much nearer the surface. Shallow reservoirs of briny liquid or slushy ice may exist within the shell, and these could also feed brief eruptions if pressure and cracks align in the right way. These two possibilities are scientifically different. A plume from the deep ocean would suggest a more direct path from the global interior to space. A plume from a shallow pocket would still be important, but it would represent a more local system within the ice shell. At present, observations do not fully resolve which source is responsible, and it is possible that different events, if they occur, need not all have exactly the same origin. The conditions of eruption on Europa would also differ from those on a world with a thick atmosphere. Here, material escaping from a vent would enter near vacuum almost immediately. Liquid water exposed directly at the surface would not remain liquid for long. It would boil, freeze, or break into vapor and ice particles depending on pressure, temperature, and speed. Any plume would therefore be a delicate and short-lived structure, not a dense cloud bank hanging in air. It would rise and disperse into space, with much of its material falling back to the surface or becoming part of the extremely thin atmosphere around the Moon. The event could be real and still difficult to catch, because its form would be fleeting. Several later observations have added related clues. Hubble measurements found persistent oxygen and hydrogen in Europa's thin atmosphere, and some scientists have argued that local hydrogen enhancements may fit with active venting in certain regions. Juno's close flyby of Europa in the 2022 dataset also provided new information about the Moon's surface and immediate environment, though it did not settle the plume question completely, taken together. Recent work supports the broader picture of Europa as an active moon where exchange between the surface and the space above may occur, yet support is not the same as final proof. The strongest current position is that Europa probably produces intermittent water vapor plumes, but their frequency, size, exact locations, and sources remain incompletely known. Geography may matter. Some of the suspected plume detections line up with regions already identified as unusual on the surface, including places where the ice appears warmer or more disrupted than the surrounding terrain. This is suggestive because a locally active region in the crust would be a plausible site for venting. If a fracture system connects to a shallow reservoir, or if tides repeatedly stress a particular zone, activity might recur there. Hubble observations that appear to indicate repeated events in roughly the same area strengthen this idea. The Moon may not vent from everywhere. It may have a small number of preferred sites, controlled by crustal weakness, tidal stress, and local heat. Tidal stress may also help explain why plumes, if real, are not always present. Europa's orbit around Jupiter causes the Moon's ice shell to flex. As the crust bends and relaxes, fractures may open slightly at some times and close at others. This changing mechanical state could determine when vapor can escape. In that picture, plume activity would not be random. It would be modulated by orbital geometry and the stress cycle within the shell. This idea remains under investigation, but it fits the broader understanding of Europa as a moon whose outer layers are continually worked by gravity. For future missions, the plume question is practical as well as scientific. Europa Clipper carries instruments designed to search for evidence of active venting, analyze gases and dust, and measure surface and subsurface conditions in far greater detail than past missions could achieve. If plumes occur during its flybys, the mission may be able to determine their composition and perhaps distinguish whether the source is deep or shallow. Even if no active plume is caught directly, the spacecraft can still search for fallout deposits, thermal anomalies, and chemical traces left behind by past events. Thus the space just above Europa is no longer treated as empty in the old simple sense. It is a place where brief releases may occur, where water from within the moon may sometimes rise into the dark and vanish again. The evidence is compelling enough to shape mission planning, yet incomplete enough to demand restraint. Europa's possible plumes stand as one of the clearest examples of how this moon reveals itself. It does not offer certainty easily. It offers signs, repetitions, hints in ultraviolet light, and a growing pattern that suggests activity just above the ice, while still leaving open the exact depth and path from which that activity comes. Beneath Europa's exposed and broken surface lies the full thickness of its ice shell, a hidden structure that cannot be seen directly but can be inferred from several lines of evidence. The visible crust gives only the upper expression of this shell. Below the ridges, pits, bands, and disrupted patches extends a larger body of ice that may be layered in strength, temperature, salinity, and behavior. Scientists study this hidden structure by combining surface geology with measurements of gravity, magnetism, thermal modeling, and the way Europa responds to tidal forcing. These methods do not yet provide a single final picture accepted in every detail. They do, however, show that the shell is not likely to be a simple block of uniform ice from top to bottom. It appears to be a complex frozen envelope above a deeper liquid layer. The first basic question concerns thickness. How much ice lies between the surface and the ocean below? This has been one of the central unknowns in Europa science for many years. Early estimates covered a wide range, from only a few kilometers to many tens of kilometers. Over time, the evidence has narrowed the more plausible range, though uncertainty remains. Most current models suggest that Europa's total ice shell is probably many kilometers thick enough to serve as a major barrier between space and ocean, yet not so thick as to prevent meaningful exchange over geological time. In broad terms, the shell is understood as substantial rather than thin in the everyday sense, but not necessarily uniform everywhere. One reason the answer is difficult is that the shell may contain more than one mechanical layer. The uppermost part is often described as a cold, brittle lid. Brittle means that the material tends to crack under stress rather than flow smoothly. This matches what is seen at the surface, where fractures, ridges, and broken blocks are abundant. Deeper down, however, conditions are warmer because heat rises from below, and because the pressure increases with depth. Warmer ice can deform more easily. Instead of breaking sharply, it may creep and flow over long periods. That means Europa's shell may be mechanically divided into a stiff outer layer and a deeper, softer layer, even if both are still made mainly of water ice. The boundary between these behaviors may shift depending on local heat and composition. This distinction helps explain why the surface can fracture while also showing signs of broader reshaping. A brittle lid can preserve cracks and displaced blocks. A softer underlying zone can allow those structures to evolve, spread, tilt, or become disrupted over time. In this view, the shell is not only a thickness to be measured, it is a vertical system with changing properties from top to bottom. The top resists and breaks. The lower part yields and flows more slowly. Between them may lie transitional regions, perhaps containing warmer ice, briny pockets, or partially melted zones. These possibilities remain under study, but they are consistent with the landforms seen above. Gravity measurements provide one way to test shell structure. A moon's gravity field reflects how mass is distributed inside it. When a spacecraft flies past Europa, small changes in its motion can reveal how the moon's mass is arranged. These measurements, combined with Europa's overall size and density, show that the Moon cannot be solid ice all the way through. It must contain denser rocky material in the interior and a lower density outer layer consistent with water and ice. Gravity data also help constrain how thick the outer water-rich layer might be. Though by themselves they do not sharply separate ice from liquid water, they are most powerful when combined with other evidence. Magnetic measurements add a different and especially important clue. When the Galileo spacecraft flew past Europa, it detected a magnetic signature that changed as Jupiter's magnetic field changed around the Moon. The simplest explanation is that Europa contains a conducting layer beneath the surface. A conducting layer is material that allows electric currents to flow. Salty liquid water is a good conductor. Solid pure ice is not. This is why Europa's induced magnetic field became one of the strongest pieces of evidence for a global ocean. Yet it also says something about the shell above that ocean. If the conducting layer lies beneath an ice shell, then the thickness and conductivity of the shell help shape how the magnetic signal appears. Magnetic data alone do not yield a single exact thickness, but they fit well with a model in which a non-conductive or weakly conductive ice shell overlies a salty ocean. Tidal behavior offers another clue. Europa is continually flexed by Jupiter's gravity because its orbit is slightly non-circular. This flexing produces deformation in the Moon's shape and stress in its outer layers. The amount of deformation depends on internal structure. A Moon with a deep liquid layer beneath a relatively decoupled shell will respond differently from a fully solid body. Observed surface fractures, large-scale tectonic features, and theoretical modelling of tidal stress together suggest that Europa's shell is at least partly decoupled from the deeper interior by liquid water below. This makes it easier for the outer shell to shift, crack, and perhaps rotate slightly over long intervals relative to the deeper rocky body. That behaviour would be hard to achieve if the shell were frozen all the way down to rock. Some researchers have also considered whether Europa's shell may vary in thickness from place to place. This is plausible. Regions with greater heat flow from below, stronger tidal dissipation, or higher concentrations of salts could maintain thinner or weaker ice locally. Other regions might be colder and thicker. A variable shell would help explain why some surface areas seem more disrupted or more chemically active than others. It would also fit the idea that plumes or shallow reservoirs, if they exist, are associated with specific zones rather than the entire Moon equally. At present, however, global thickness variations are not mapped with certainty. The possibility is strong, but the details remain unresolved. Brines complicate the picture further. If the ice shell contains pockets or layers of salty liquid, partially melted slush, or ice rich in impurities, then the shell is not simply a clean frozen barrier. Salts lower the freezing point of water and change both density and conductivity. Small amounts of briny material could therefore influence how the shell deforms, how it exchanges chemicals with the surface, and how it appears in geophysical measurements. Such brines may not be everywhere, and they may not form large continuous layers. Still, they help explain why Europa's shell is often described as structured rather than uniform. The total thickness of the shell remains one of the key targets of future missions. Radar sounding from Europa Clipper is designed in part to probe the ice and search for internal layering, pockets of liquid, and the depth of major boundaries. This will not necessarily provide a perfectly complete map, because radar performance depends on ice properties and interference from rough or chemically complex terrain. Even so, it offers the best near-term opportunity to move from inference toward direct subsurface sounding. Results may show that the shell includes buried fractures, stacked layers, local lakes, or deep interfaces not previously resolved. what can be said now with confidence is more modest and more important. Europa's outer shell is real, substantial, and structurally complex. It is thick enough to separate the surface from the ocean by a major frozen barrier. It is also dynamic enough to crack, shift, and perhaps permit exchange over time. The shell likely includes a cold, brittle lid above warmer, softer ice, with possible local brines and thickness variations superimposed on that general pattern. Beneath the bright, marked surface, the ice is not a featureless wall. It is a hidden architecture of layers and changing properties, a frozen intermediary between the hard vacuum of space above and the dark liquid world below. Below Europa's layered ice shell lies the central hidden feature that has made the Moon one of the most compelling worlds in planetary science, a global ocean of liquid water. This ocean is not directly visible. No camera has seen it open to the sky. No probe has descended through the crust to touch it. Yet the case for its existence is now strong. It rests on several independent lines of evidence that point toward the same conclusion. Beneath the frozen exterior, Europa almost certainly contains a vast body of salty liquid water extending around the Moon. In simple terms, Europa is not a solid ball of ice. It is an ocean world. The first clues came from the Moon's surface itself. Europa's exterior is cut by fractures, bands, and disrupted terrains that suggest motion, separation, and local renewal. These features imply that the ice shell has been active, and that something beneath it allows or drives that activity. A fully rigid frozen body would not respond in quite the same way, but surface features alone could not prove a deep ocean. The stronger evidence arrived through measurements of magnetism. During its flybys in the 1990s, NASA's Galileo spacecraft detected changes in Europa's magnetic environment that were best explained by a conducting layer inside the Moon. Because salty liquid water conducts electricity well, this became one of the most powerful signs that a global ocean lies beneath the ice. The logic of the magnetic evidence is careful and elegant. Jupiter has a large magnetic field that changes as Europa moves through it. If Europa contains a conductive layer, changing magnetic conditions around the Moon will induce electric currents in that layer. Those currents, in turn, create a secondary magnetic field that can be measured by a spacecraft. Galileo detected exactly such a response. Scientists examined alternative explanations, but the simplest and most consistent one was a global salty ocean under the surface. The outer ice alone could not account for the signal. A rocky interior alone could not account for it either. A layer of liquid salt water could. Gravity and density measurements support the same broad picture. Europa's overall density shows that it's made partly of rock and partly of water-rich material. It is denser than a pure ice body, which means a significant rocky interior must be present. At the same time, it is not as dense as a fully rocky world of similar size. This requires an outer layer of water and ice. When the thickness of that outer water-rich layer is estimated from models combining density, gravity, and magnetic data, the result is large enough to include both an ice shell and a substantial ocean beneath it. The exact dimensions remain uncertain, but the general structure is now widely accepted. This ocean is thought to contain more water than all of Earth's surface oceans combined. That comparison appears often because it gives a sense of scale, though the European Ocean is very different from Earth's seas. On Earth, oceans lie under air and sunlight, with waves above and a broad exchange with the atmosphere. On Europa, the ocean is sealed beneath many kilometers of ice, cut off from direct sunlight and exposed instead to immense pressure. It is not a blue surface under the sky. It is a dark global sea hidden under a frozen roof. Its upper boundary is the underside of the ice shell. Its lower boundary is the rocky interior of the Moon. The depth of this ocean is still estimated rather than measured directly, but many models suggest it may be on the order of tens of kilometers deep. That is enough to make it not merely a thin layer, but a true planetary ocean. It likely surrounds most or all of the Moon, rather than existing as isolated regional seas. This global extent matters. A world-spanning ocean allows large-scale circulation, wide chemical exchange, and long-term stability in ways that local pockets of liquid might not. The image that emerges is of Europa as a three-part system: a rocky inner body, a deep global ocean, and an outer shell of ice. For such an ocean to remain liquid so far from the Sun, a source of internal heat is required. Sunlight alone is far too weak at Jupiter's distance to maintain a liquid sea beneath the ice. The most important heat source is thought to be tidal heating. As Europa moves along its slightly stretched orbit, Jupiter's gravity flexes the Moon. That repeated flexing generates heat inside the body, especially in regions where materials deform under stress over immense timescales. This process can supply enough energy to help prevent the internal water layer from freezing solid. Radiogenic heat from the decay of elements in the rocky interior may also contribute, but tidal heating is generally considered the dominant source in keeping Europa's interior active. The ocean is also thought to be salty. Salt is important for several reasons. It lowers the freezing point of water, making liquid conditions easier to maintain. It also increases electrical conductivity, which helps explain the magnetic data. These salts may come from long interaction between water and the rocky seafloor, where minerals dissolve into the ocean over time. Surface observations showing salts and carbon-bearing compounds in some disrupted terrains are often interpreted as indirect support for this picture. If material from the ocean or from ocean-connected reservoirs reaches the surface, then the chemistry observed above may preserve hints of the hidden sea below. Even with strong evidence, uncertainties remain. Scientists still debate the exact thickness of the ice shell above the ocean, the exact salinity of the water, and the details of how the ocean circulates. It is also not yet fully clear how directly the ocean communicates with the surface. In some models, exchange occurs through fractures, partial melting, or rising brines over geological time. In others, the connection is more limited and episodic. These questions matter because the value of the ocean is not only that it exists, but that it may participate in a larger chemical system connecting rock below, water in the middle, and oxidized materials above. The physical conditions within the ocean are unlike those of shallow water on Earth. Sunlight does not penetrate through the thick ice shell. Photosynthesis, the use of sunlight by living systems to build chemical energy, would therefore not operate in the ordinary surface ocean sense. The water would exist in perpetual darkness. Pressure would increase with depth. The temperature would likely remain near the freezing point set by pressure and salinity in the upper parts, with warmer conditions possible nearer the seafloor where internal heat enters the system. The ocean would not be still. Convection and circulation likely move water slowly through the global sea, redistributing heat and dissolved substances over time. What makes this ocean so important is not just its size, but its persistence. Evidence suggests that Europa has maintained internal liquid water for a very long span of geological time. A temporary ocean would be scientifically interesting. A long-lived one is more consequential. Time allows chemistry to unfold. Time allows contact between water and rock to alter minerals and release dissolved compounds. Time allows energy gradients to remain available. In planetary habitability studies, duration matters as much as presence. Europa's ocean appears not to be a brief exception, but an enduring feature of the Moon's interior. Thus the path inward reaches a concealed world of extraordinary scale. Beneath the frozen crust of Europa lies a dark, salty, global ocean held liquid by the repeated gravitational working of Jupiter and neighbouring moons. It is hidden from direct view, yet strongly supported by magnetic, gravitational, and geological evidence. It circles the Moon in silence below the ice, separated from space by a cold shell and from the rocky interior by a deep boundary where water meets stone. Here, in this unseen sea, the idea of Europa changes from a bright icy moon into something far more complex, a water world enclosed in darkness, stable enough to endure, large enough to matter, and strange enough to remain one of the clearest places beyond Earth where the conditions for life may exist. Europa's hidden ocean is not important only because it is liquid. Water alone does not make a world biologically interesting. A vast dark sea of perfectly pure water, sealed away from chemistry and energy, would offer much less promise than a smaller ocean rich in dissolved substances and active gradients. What makes Europa's ocean scientifically compelling is the growing possibility that it contains salts, carbon-bearing compounds, and chemical imbalances capable of supporting reactions over long spans of time. In simple terms, the ocean may not be chemically blank, it may be active water. Salts are central to this idea. A salt is a mineral compound that dissolves in water and separates into charged parts called ions. These ions affect how water behaves. They change its freezing point, its electrical conductivity, its density, and the kinds of reactions it can support. Evidence from magnetic measurements already suggests that Europa's ocean must be conductive, which strongly implies dissolved salts. Surface observations strengthen that interpretation by showing salt-bearing material in disrupted regions of the ice shell, especially in places where material may have reached the surface from below. The exact mixture remains uncertain, but the basic conclusion is firm. Europa's ocean is unlikely to be pure water. It is more likely a mineral-rich sea. The identity of those dissolved salts matters because different mixtures point to different histories. An ocean rich in sulfates would suggest one path of water-rock interaction and one balance of oxidation. An ocean richer in chlorides would suggest another. Recent surface interpretations have made chloride salts especially important, raising the possibility that sodium and chloride may be significant components of the interior water. This does not make Europa an exact twin of Earth's oceans. The pressures, temperatures, and planetary context are entirely different. Yet it does mean that Europa's water may be chemically familiar in one limited but meaningful sense. It may be a salty sea formed through long contact between water and rock. That contact is critical. At the bottom of Europa's ocean lies a rocky interior, where liquid water meets rock over long periods. Minerals can dissolve, react, and transform. On Earth, such interaction shapes the chemistry of the oceans and creates environments where energy becomes available through chemical exchange. On Europa, similar principles may apply even though the details remain hidden. Water passing through cracks, pores, or altered layers of rock can pick up dissolved ions, metals, and gases. It can also participate in reactions that generate reduced compounds, substances rich in electrons and therefore capable of later reacting with oxidants. The ocean, in that sense, may be chemically fed from below. At the same time, Europa's surface may provide another part of the chemical system from above. The Moon's outer ice is exposed to intense radiation from Jupiter's magnetosphere. That radiation breaks apart water molecules and other compounds at the surface. producing oxidants such as molecular oxygen and related reactive substances. An oxidant is a substance that tends to accept electrons in a chemical reaction. On Earth, oxygen plays this role in many living systems. At Europa, oxidants formed at the surface would not matter much if they remained trapped forever in the irradiated outer skin. Their importance depends on transport. If some fraction of these surface-made oxidants can move downward through fractures, recycling, melting, or convection in the ice shell, they could eventually enter the ocean. This possibility creates one of the most interesting ideas in Europa science. The ocean may receive chemically reduced material from below, where water interacts with rock, and chemically oxidized material from above, where radiation alters the surface. If both sources are present, and if they are brought into contact, a chemical gradient is created. A gradient is a difference between two states, such as a difference in composition or energy level. Life on Earth depends heavily on gradients. Cells make use of differences in chemistry to perform work, build structure, and maintain themselves. Europa's ocean may contain the same general kind of opportunity, even though the specific substances and pathways may differ. Carbon adds another layer to this picture. Observations have shown carbon dioxide on Europa's surface, especially in regions where recent exposure of internal material is suspected. Carbon is one of the main building elements of known life, not because it is rare, but because it forms versatile bonds and can participate in many stable and complex molecules. The presence of carbon-bearing compounds does not mean life exists, but it does remove one barrier to habitability. A habitable environment requires not only water and energy, but access to the key chemical elements needed to build and sustain complex chemistry. Europa now appears increasingly likely to possess those ingredients in some form. Nitrogen, phosphorus, sulfur, and trace metals are also important in biology as it is known on Earth, though they are harder to constrain remotely at Europa. Models of water-rock interaction suggest that at least some of these elements could be present in the ocean, released from the rocky interior or incorporated during the Moon's formation. Their abundance remains uncertain. This uncertainty is normal. Europa's ocean has not yet been sampled directly. Much of what is inferred depends on analogy, modeling, and the chemistry of materials seen at the surface. Still, the ocean is no longer viewed as a chemically featureless reservoir. It is viewed as a place where dissolved substances are likely abundant enough to matter. Energy sources within the ocean may come in several forms. Tidal heating maintains the broader internal activity of the Moon, but biological or pre-biological chemistry usually depends on more local and usable energy gradients. Water circulating through warm rock can create such gradients. Oxidants entering from above could create others. Differences in temperature, pressure, salinity, and mineral content might all contribute. None of this guarantees that life emerges. It means only that the ocean may possess the kind of chemical imbalance that life could exploit if suitable systems arose, a completely balanced environment, where everything had already reacted as far as possible, would offer little free energy. Europa may avoid that stillness through continuous supply from both seafloor and surface. The degree of communication between these regions remains uncertain. If the ice shell is very thick and transport through it is inefficient, then oxidants made at the surface may enter the ocean only slowly. If the shell contains active recycling zones, fractures, or briny pathways, transport could be more substantial. Likewise, reduced compounds generated near the rocky floor may remain near the bottom, unless circulation carries them upward. The habitability of Europa's ocean therefore depends not only on what chemicals exist, but on how they move. An ocean can be chemically rich overall, and still be limited in biologically useful exchange if its components remain isolated from one another? This is one of the major open questions. Even with these uncertainties, the broad picture is striking. Europa likely contains a long-lived salty ocean. That ocean probably interacts with the rock below. The surface above produces oxidants through radiation. Carbon-bearing material is present. Heat enters the system through tidal and internal processes. Taken together, these factors suggest a world where chemistry does not merely sit in storage. It circulates, accumulates, and remains out of equilibrium. In planetary science, such disequilibrium is important because it means usable energy may exist. Reactions remain possible. The ocean can change. Thus, the inward path reaches not just liquid water, but a chemically promising sea. Europa's ocean may hold dissolved salts from long contact with rock, carbon-bearing substances that broaden its chemical inventory, and gradients of oxidation and reduction that provide potential energy. It may be fed from below by the seafloor and from above by the irradiated crust. Not all details are known. The exact salinity, composition, and transport rates remain under study. Yet the central idea is now clear enough to guide missions and theory alike. Europa's ocean is not merely a hidden body of water. It is a hidden chemical system, one that may be active enough, diverse enough, and energetically uneven enough to support the next deeper question about life. At the bottom of Europa's ocean lies the rocky interior, a hidden floor where water meets stone under great pressure and in complete darkness. This boundary is one of the most important regions in the Moon's internal structure because it is where heat, minerals, and chemical change are most likely to enter the ocean from below. The surface above may be cold and exposed to radiation, but here the conditions are different. The ocean rests on rock, and that contact transforms the idea of Europa from a frozen shell over water into a working planetary system. In this deep region, the Moon's internal energy interacts with its ocean directly. Europa is thought to have a differentiated interior. This means its materials separated into layers early in its history, with denser rocky and metallic material moving inward, and lighter, water-rich material remaining farther out. Most models describe a metallic core deep within the Moon, surrounded by a rocky mantle, with the global ocean lying above that rocky layer and the ice shell above the ocean. The exact size of the metallic core remains uncertain, but the presence of a rocky interior is well supported by the Moon's density. That rocky body is not inert in the broad geological sense. It holds heat from radioactive decay and responds to the tidal forces imposed by Jupiter and the orbital resonance with neighbouring moons. Tidal heating is one of the key processes shaping Europa's interior. As Europa travels around Jupiter on its slightly stretched orbit, the strength and direction of Jupiter's gravitational pull vary over the course of each orbit. The Moon is therefore flexed repeatedly. This flexing is not confined to the ice shell. It affects the entire body. Wherever materials deform under stress, heat can be produced. In the ice shell, this helps maintain warmth and mobility in deeper layers. In the rocky interior, tidal distortion may also generate heat, especially if the rock is fractured, heterogeneous, or partially altered by past water interaction. The exact distribution of this heating remains uncertain, but it is likely that Europa's interior has not been thermally quiet over geological time. Radiogenic heating also contributes. Certain elements within rock decay naturally and release energy. This process is slower and steadier than tidal heating, and in a smaller body like Europa, it is not thought to dominate in the way it can within larger planets. Even so, it adds background heat to the rocky interior. When combined with tidal energy, It helps sustain the thermal contrast needed for long-lived contact between water and warm rock. What matters biologically and chemically is not simply the total amount of heat, but whether enough heat reaches the water-rock boundary to maintain reaction zones, circulation, and gradients in temperature and composition. Where liquid water interacts with rock, geochemistry begins. Water can move through pores, fractures, and altered minerals in the upper part of the rocky seafloor. It can dissolve ions, carry them upward, and react with minerals in ways that change both rock and fluid. On Earth, such water-rock interaction is fundamental to ocean chemistry and to many deep environments where life thrives without sunlight. Europa is not Earth, but the same broad principles of chemistry apply. A rocky seafloor under a global ocean is not just a passive base. It is a place where materials exchange, where minerals can be altered, and where chemically useful compounds may be generated. One process often discussed in this context is serpentinization. This term refers to a set of reactions in which certain water-rich interactions alter iron and magnesium-bearing rocks, producing new minerals and sometimes releasing hydrogen. Hydrogen is important because it is a reduced molecule, rich in electrons and capable of serving as a source of chemical energy in reactions with oxidants. On Earth, hydrogen produced by water-rock interaction supports microbial communities in some deep environments. Whether Europa's rocky floor undergoes serpentinization on a large scale is not yet known, because the composition and temperature of its mantle are not directly measured. Still, the process is plausible enough to be taken seriously in models of European habitability. Another important possibility is hydrothermal activity. A hydrothermal system forms when water circulates through heated rock and returns altered, often carrying dissolved minerals, gases, and thermal energy. On Earth, hydrothermal vents on the seafloor create some of the most chemically dynamic habitats known, including environments that support life independent of sunlight. The idea of hydrothermal vents on Europa is therefore especially compelling. If heat from tidal and radiogenic sources is focused in parts of the rocky mantle, and if ocean water can circulate through those regions, then vent-like systems may exist on the European seafloor. These would not necessarily resemble every vent on Earth, and their abundance, strength, and lifetime remain uncertain. Yet even modest hydrothermal circulation could have large consequences for ocean chemistry. The presence of such activity depends on several factors. The rocky interior must be warm enough in at least some places to drive circulation. Water must be able to reach reactive rock. The structure of the seafloor must permit exchange rather than forming a sealed inert boundary. Current evidence does not prove active vents directly, but it supports a world in which such systems are plausible. Models of Europa's internal evolution suggest that water-rock interaction could have been occurring for immense spans of time. If so, the ocean above would have had a long opportunity to accumulate dissolved minerals and sustain chemical disequilibrium. Heat from the seafloor would also influence ocean circulation. Warmer water tends to rise, colder water tends to sink, and salinity changes can further complicate the pattern. This means the deep ocean is unlikely to be motionless. Heat entering from below can help drive convective circulation through the water column, transporting dissolved substances away from the seafloor and redistributing them through the global ocean. Such motion is important because it links local energy sources to the broader interior environment. A vent or warm reactive patch at the bottom matters much more if its chemical products are mixed into the ocean rather than remaining trapped near the rock. The nature of Europa's rocky interior itself is another important unknown. It may be fractured and hydrated in places, altered by long contact with water, or partly differentiated into layers of differing mineral composition. It may include zones that have cooled and stiffened and others that remain more active. The exact mineralogy affects what compounds can be released into the ocean. Iron, magnesium, sulfur-bearing minerals, silicates, and trace metals all shape the chemical possibilities of the seafloor environment. Without direct samples, scientists rely on density models, meteorite analogues, and theoretical evolution studies. These approaches do not provide certainty, but they strongly suggest that Europa's ocean rests on a chemically interesting foundation, rather than on an inert frozen base. This deep region also determines how long Europa can remain active. If tidal and internal heating continue to maintain interaction between rock and water, then the seafloor can remain a sort of chemical renewal over geological time. If that interaction weakens, the ocean may become less dynamic even if it remains liquid. Thus, the seafloor is not only a place of present chemistry, it is part of the Moon's long-term habitability. A world with water but no lasting contact with reactive rock would be poorer in possibilities. Europa appears more promising because the ocean likely touches stone directly and has done so for a very long time. Nothing in this deep setting is visible from above. No light reaches it from the sun. No camera has yet seen its contours. Yet the logic of the Europa's interior leads steadily toward it. Beneath the ice shell and beneath the global ocean lies a rocky sea floor warmed by tidal and internal heat, shaped by long contact with water and capable of generating chemical energy through water-rock interaction. Hydrothermal activity remains unconfirmed but plausible. Hydrogen generation remains unmeasured, but possible. Mineral exchange is expected. The deep interior is therefore not a mere boundary. It is the engine room of Europa's ocean world, the place where heat enters from below, and where the strange dark sea above may receive the energy and ingredients needed to remain chemically alive. A world may contain water and still remain lifeless. A world may contain energy and still never develop biology. This is why scientists speak carefully about habitability. Habitability does not mean that life is present. It means that the known conditions required for life, or for chemistry that could lead toward life, may exist. On Europa, this distinction is essential. The Moon is not treated as a proven living world. It is treated as a place where the ingredients and environmental conditions for life may be present beneath the ice. The question is not whether Europa looks alive from the outside. The question is whether its hidden interior provides a stable setting where life could persist. In astrobiology, habitability is often approached through a small set of basic requirements. The first is liquid water. On Europa, this requirement appears to be met by the global ocean beneath the ice shell. The second is access to essential chemical elements. Water alone is not enough. Life as it is known on Earth also depends on carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, and a range of metals and trace compounds. Some of these are clearly present or strongly inferred at Europa. Water ice provides hydrogen and oxygen. Surface and near-surface observations show carbon-bearing compounds and salts. Models of the rocky interior suggest that other biologically useful elements may be released through water-rock interaction. The exact inventory remains uncertain, but the environment is no longer imagined as chemically empty. The third requirement is energy. Life needs a continuous source of usable energy to build and maintain structure, to grow and to reproduce. On Earth, surface life depends heavily on sunlight, either directly through photosynthesis or indirectly through food chains built on photosynthetic organisms. Europa's ocean lies beneath thick ice, cut off from sunlight. If life exists there, It would not depend on light from the sun in any ordinary way. Its energy would need to come from chemistry. This is one reason Europa interests scientists so strongly. The Moon appears capable of sustaining chemical gradients that could provide such energy. Reduced compounds may rise from the seafloor where water interacts with rock. Oxidants may be produced at the surface by radiation and transported downward over time. If these materials meet within the ocean, they create opportunities for reactions that release energy. The fourth requirement is time. Habitability is not only about ingredients gathered in one moment. It is about whether those ingredients remain available long enough for complex chemistry to organize itself and persist. Europa's ocean is thought to be ancient on geological timescales. It may have existed for a very long portion of the Moon's history. That long duration matters because chemical systems need time to develop. Even on Earth, life did not appear instantly after the planet cooled. A world that remains wet, chemically active, and energetically supplied over immense spans is more promising than one that experiences only brief episodes of favorable conditions. Europa appears to belong to the first category. Yet habitability also depends on connection. A world can possess water, chemistry, and energy in separate compartments and still be less favorable if those components rarely interact. This is one of the most important uncertainties at Europa. Scientists do not yet know how efficiently surface oxidants reach the ocean. They do not know how widely hydrothermal or water rock reactions operate across the sea floor. They do not know how quickly ocean circulation mixes dissolved compounds from one region to another. Habitability, in this deeper sense, depends on transport. The ingredients of life must not only exist, they must be brought into contact in ways that keep the environment out of chemical balance. Life uses imbalance. It draws on differences in energy, composition, and concentration. Europa may provide these differences, but the rate and extent of exchange are still not fully known. Temperature also shapes the question. Europa's surface is far too cold and too strongly irradiated to be regarded as a likely long-term home for complex biology. The hidden ocean below, however, may be more moderate. Moderate does not mean warm in the everyday human sense. It means that liquid conditions are maintained, and that local environments near the seafloor or within active regions may support chemistry without freezing solid. Even small temperature differences matter because they affect reaction speed, fluid movement, and the behavior of dissolved compounds. In a dark ocean world, the places most relevant to life may not all be equally suitable. Habitability may vary from region to region, with some zones more chemically active than others. The word habitable itself can therefore mislead if used too casually. It does not imply forests, animals, or any landscape resembling Earth's surface. In the context of Europa, habitability points toward the possible existence of microbial-scale environments, perhaps comparable in a broad sense to Earth's deep ocean ecosystems, subsurface microbial habitats, or hydrothermal settings where life survives without sunlight. Even this comparison must be made carefully. Europa is colder, more isolated and more strongly controlled by an icy shell and Jovian tides than any ocean on Earth. If it is habitable on its own terms. Scientists also distinguish between local habitability and global habitability. A global ocean may exist, yet only certain parts of it may have the right balance of energy and chemistry to support life. Near the seafloor, hydrothermal processes might create especially rich conditions. In the mid-ocean interior, circulation might distribute nutrients more thinly. Near the underside of the ice shell, oxidants descending from above might accumulate. Some regions may be more favorable than others, and these favorable zones may change over time. Europa need not be uniformly habitable in order to matter. A small number of stable chemically active niches would already be of profound significance. Another important point is that habitability can exist without life ever beginning. The origin of life is a separate question from the maintenance of life. A world may offer suitable conditions and still never produce living systems. Conversely, life may arise under one set of conditions and later survive under another. At Europa, scientists can presently assess only the environment, not the biological outcome. Missions such as Europa Clipper are designed primarily to evaluate habitability, not to detect organisms directly. They will examine the ice shell, the chemistry of the surface, the possibility of plumes, the structure of the ocean system, and the exchange between surface and interior. These measurements help answer whether Europa has the conditions life requires, even if they do not answer whether life actually exists there. This disciplined approach is one of the strengths of Europa science. It resists turning possibility into conclusion. The evidence supports a salty ocean, a rocky seafloor, internal heat, chemical diversity, and potential energy sources. Together these make Europa one of the most promising habitable environments beyond Earth in the solar system. At the same time, major unknowns remain. The ocean's exact composition is not known. The thickness and behavior of the ice shell are not fully resolved. The transport of oxidants and organics is uncertain. The strength and distribution of seafloor activity are inferred rather than directly observed. These uncertainties do not weaken the case for habitability, they define its boundaries. So the concept of habitability on Europa settles into a careful form. It is not a claim of inhabited seas. It is not a promise of discovery. It is a scientific judgment based on water, chemistry, energy, and time. Beneath the bright frozen exterior, Europa appears to possess the essential framework that life could use. The ocean may be long-lived, the chemistry may be rich enough, the gradients may be strong enough. The deep interior may keep supplying energy from below, while the surface contributes oxidants from above. Whether these conditions have ever crossed the threshold into biology remains unknown, but by the standards of planetary science, Europa stands as a world where the environment itself has moved close to that threshold, and where the hidden ocean may be one of the clearest natural settings in which life could exist beyond Earth. If life exists in Europa's hidden ocean, it is unlikely to resemble the life most familiar from Earth's surface. It would not live beneath sunlight. It would not depend on leaves, warm air, or open water under the sky. It would exist, if it exists at all, in darkness, beneath a roof of ice, within a cold ocean shaped by pressure, chemistry, and rock below. For this reason, the most realistic scientific approach is not to imagine large creatures or visible ecosystems, but to consider the simplest forms of life and the most basic ways they might obtain energy. The question is not how Europa could support familiar biology. The question is what kind of strange but plausible life pathway could function there at all. On Earth, many living systems depend directly or indirectly on sunlight. Plants, algae, and some microbes capture light and convert it into stored chemical energy. Animals and many other organisms then depend on those primary producers. Europa's ocean cannot operate in this way. Sunlight does not penetrate through the thick ice shell to the water below. Any Europan life would therefore have to rely on chemosynthesis, a process in which organisms build usable energy from chemical reactions rather than from light. This is not an exotic idea invented only for distant worlds. On Earth, chemosynthetic microbes live in dark places such as hydrothermal vent systems, deep subsurface rock, and other isolated environments. Their existence shows that biology does not require sunlight everywhere. It requires a source of usable chemical energy. The most plausible Europan metabolisms, if life is present, would therefore be microbial and chemical. A metabolism is the set of reactions by which a living system takes in energy and matter, uses them to maintain itself, and produces waste. On Europa, scientists often consider reactions involving hydrogen, sulfur compounds, carbon dioxide, methane, and oxidants such as oxygen-bearing molecules. For example, if water-rock interaction at the seafloor produces hydrogen, and if oxidants generated at the surface are transported into the ocean, then microbes could in principle gain energy by combining those substances in controlled reactions. On Earth, some microbes do exactly this, using hydrogen as an energy source and carbon dioxide as a carbon source. This does not prove that Europa hosts such organisms. It shows that the chemistry thought possible there is compatible with known biological strategies. Methanogenesis is one frequently discussed example. In this process, microbes use hydrogen to reduce carbon dioxide and produce methane. On Earth, methanogens live in oxygen-poor environments such as sediments, wetlands, and parts of the deep subsurface. They are among the most ancient metabolic types known. A Europan version, if one existed, would not necessarily be identical to terrestrial methanogens. But the general pathway is scientifically attractive because it relies on materials that may plausibly exist in Europa's ocean. Another possibility involves sulfur-based metabolisms, where reduced sulfur compounds from rock interaction are combined with oxidants. Iron-based reactions are also conceivable if iron-bearing minerals interact with water and become available in usable forms. The exact chemistry depends on what compounds are present in sufficient abundance and whether they remain in contact long enough to sustain living systems. The strangeness of Europan life, if real, would therefore not come from violating chemistry, but from the particular way chemistry would be arranged in that dark ocean. It might live slowly, in a cold environment with limited energy flux. Biological processes could proceed at rates far slower than those common in warm sunlit ecosystems on Earth. Growth might be sparse, populations might remain thinly distributed, cells might divide rarely, conserve energy carefully, and persist for long periods in near-dormant states between moments of greater opportunity. On Earth, some deep subsurface microbes already live under severe energy limitation and can survive with extraordinary patience. Europa may favour similar endurance over speed. Another strange possibility is that Europan life, if it exists, may cluster only in certain zones rather than filling the entire ocean. The ocean is global, but energy sources may be local. Hydrothermal regions at the seafloor could provide concentrated chemical gradients. The underside of the ice shell might provide another kind of niche if oxidants descend from above and accumulate there. Regions where ocean circulation brings together different water masses could also matter. Life may therefore be patchy, sparse, and highly dependent on boundary zones where chemistry is out of balance. This would make Europa biologically significant while still leaving most of the ocean relatively poor in energy. A living world need not be uniformly rich in life. The form of Europan organisms, if they exist, would most likely be microscopic. Large, complex multicellular life requires abundant and stable energy, long evolutionary development, and often ecological structures that support higher levels of organization. Europa may not provide these conditions, or may provide them only weakly. The scientific focus therefore remains on microbes or microbe-like systems. These would be small enough to exploit narrow chemical gradients, flexible enough to survive scarce resources, and simple enough to emerge in an isolated ocean if life ever began there. Even such organisms, however, would be remarkable. A single independent biosphere based on dark ocean chemistry would transform the understanding of life in the universe. Membranes, internal chemistry, and information-carrying molecules in Europan life need not be identical to those of Earth life, though many scientists expect that the basic constraints of chemistry would still favour certain familiar solutions. Liquid water supports dissolved ions and polar molecules well. Carbon remains the most versatile known element for building complex stable structures. Cells or cell-like boundaries are useful because they separate internal chemistry from the external environment and allow gradients to be controlled. Thus, Europan life could be alien in origin and still convergent in broad design, using water, carbon chemistry, membranes, and catalytic molecules because those are efficient solutions, not because of any direct connection to Earth. At the same time, some features could differ sharply. Europa's ocean may have different salt balances, pressures, and oxidant levels from any environment on Earth. Its history is more isolated, its energy sources are likely weaker and more unevenly distributed. If life arose there independently, it might use unusual biochemical pathways, unusual membrane compositions, or different strategies for repairing radiation-damaged or oxidant-exposed molecules if transported toward the ice shell. It might also exist only in forms adapted to long-term scarcity, with metabolisms tuned to exploit fleeting pulses of chemical opportunity. The strangeness of the Europan life would most likely lie in these details of survival, not in dramatic visible appearance. Scientists also consider the possibility that Europa is habitable yet sterile, or that it contains only prebiotic chemistry. Prebiotic means chemistry that has not crossed into life, but includes molecules and reactions relevant to life's origin. In a dark ocean rich in salts, carbon compounds, and redox gradients, complex molecules might form, accumulate, and interact without ever becoming living systems. This would still be scientifically profound. It would show that chemistry can approach biology in hidden ocean worlds even if full life does not emerge. Europa therefore matters not only as a possible home of life, but as a place where the boundary between non-living chemistry and living systems may be explored indirectly. Any search for Europan life must also avoid a common mistake assuming that unfamiliar conditions require dramatic speculation. The most grounded scientific expectation is modest. If Europa hosts life, it is likely microbial, chemically powered, sparse, and localized. It may resemble Earth's deep dark biosphere more than any surface ecosystem. It may survive on hydrogen, sulfur, iron, or other redox pairs. It may persist near the seafloor, near the underside of the ice, or wherever transport brings oxidants and reduced compounds together. It will be strange not because it breaks the rules of life, but because it follows those rules in a world so hidden and severe. Thus the inward path reaches the threshold of biology and remains careful there. Europa's possible life pathways are constrained by darkness, cold, chemistry, and time. They point toward microbes, chemosynthesis, slow metabolism, and local niches shaped by rock-water interaction below and oxidants from the surface above. Nothing in present evidence confirms that such life exists. Yet the known chemistry and physics of the Moon make these pathways plausible enough to study seriously. If life has found a way into Europa's ocean, it is likely simple, patient, and deeply unlike the living world most familiar on Earth, while still resting on the same fundamental requirement that all life must meet the steady ability to capture usable energy from its surroundings and endure. The newest clues about Europa do not arrive as a single discovery. They emerge as a pattern formed from several kinds of evidence, each incomplete on its own, more persuasive when considered together. Surface chemistry, magnetic measurements, geological mapping, plume studies, thermal modeling, and new spacecraft planning all point toward the same broad conclusion. Europa is not merely an icy moon with an interesting appearance. It is an active ocean world whose hidden interior may possess the ingredients and conditions required for life. The strength of this conclusion lies not in certainty about every detail, but in the growing agreement among different methods of study. One of the clearest recent developments concerns carbon. Observations from the James Webb Space Telescope identified carbon dioxide concentrated in specific regions of Europa's surface, especially in geologically disturbed terrain where material from below may have reached the exterior. This matters because carbon is one of the essential elements of known life, and because the geological context suggests that at least some of that carbon-bearing material may be linked to the moon's interior rather than being delivered only by impacts from space. Scientists remain careful here. Carbon dioxide at the surface does not prove anything biological. It does, however, strengthen the case that Europa's ocean system includes key chemical ingredients, and that these ingredients can become visible in regions where the crust has been disrupted. Another important line of evidence concerns the chemistry of salts at the surface. Newer interpretations increasingly favor chloride salts in at least some regions, rather than only sulfate-rich compositions. This shift matters because chloride-rich chemistry may indicate a different kind of ocean than earlier models often assumed. It suggests that the hidden sea could be chemically compatible with long-term water-rock interaction in ways that preserve dissolved salts more similar in broad type to some terrestrial marine environments, though Europa remains distinct in every major planetary condition. Again, the meaning is careful rather than dramatic. No single salt detection reveals the full ocean composition, yet each improvement in surface chemistry helps narrow the possibilities and refine the picture of the sea below. The possibility of plumes remains one of the most discussed recent clues. Hubble observations and related follow-up studies continue to support the idea that Europa may at times release water vapor above the surface. These detections are intermittent and not uniformly confirmed in every observation. This is why scientists still speak of possible or probable plumes, rather than of permanent established jets. Even so, the pattern is strong enough to shape mission planning. If material does escape from Europa into space, even briefly, it offers a rare opportunity to study internal chemistry without penetrating the ice shell directly. The exact source remains uncertain. Some plumes, if real, may rise from shallow briny reservoirs within the shell. Others may connect more deeply. This uncertainty is not a flaw in the science. It is part of the current boundary between observation and interpretation. Surface geology also continues to gain meaning as new images and reanalysis improve understanding. Regions of chaos terrain, double ridges, and disrupted blocks are no longer viewed only as curious landforms. They are treated as records of a shell that may exchange material with deeper layers, at least episodically. Some recent work on double ridges suggests that shallow pockets of water or slush may have formed beneath the surface and shaped the ice above. This is important because it offers a mechanism by which material can move within the shell, bridging the gap between the deep ocean and the exposed crust. It does not prove direct pathways from seafloor to surface in every case. It does show that the shell may be more dynamic and locally permeable than a simple frozen barrier would suggest. The coming missions are designed to test these ideas in a disciplined way. NASA's Europa Clipper mission is the central effort, It is built not to land, but to perform repeated close flybys, using instruments designed to map surface composition, study the ice shell, search for plumes, measure the magnetic environment, sound the subsurface with radar, and identify regions where ocean surface exchange may be occurring. ESA's JUICE mission, while focused primarily on Ganymede, also includes flybys of Europa that will add valuable context and comparative information. Together, these missions represent the next major step in Europan science. They are not designed to announce life. They are designed to determine how habitable Europa truly is, how thick and structured its shell may be, how active its surface remains, and how chemistry is distributed across the Moon. This distinction is essential. The search at Europa is not yet a search for organisms in the direct sense. It is a search for environmental truth. Scientists want to know whether the Moon's ocean receives oxidants from above, whether its seafloor likely sustains water-rock interaction below, whether carbon, salts, and perhaps organics are available in meaningful amounts, and whether pathways exist for these components to meet. Habitability is a scientific threshold. Europa appears to be approaching or perhaps crossing that threshold, but the data must establish how strongly and in what regions. There are also hard limits to what current and near-future missions can conclude. Remote sensing can detect composition, structure, temperature variations, and magnetic effects. It can reveal plume particles if a spacecraft passes through them. It can identify places where the ice shell is unusual or where fresh material may be exposed. Yet it cannot, by itself, settle every question about the ocean's full chemistry or the exact state of the seafloor. It also cannot easily detect sparse, deep microbial life hidden beneath kilometers of ice. A direct search for life would likely require future landed missions or eventually some form of access to the subsurface, tasks far beyond present engineering plans. This is why the language of current missions remains careful. They are preparing the ground for better questions, not claiming final answers before the evidence is ready. Still, the direction of the evidence has changed the status of Europa in planetary science. It is no longer treated as one speculative possibility among many icy moons. It stands near the center of astrobiological interest because it unites the key elements of a potentially habitable environment: a global ocean, a rocky floor, internal heat, surface oxidants, carbon-bearing compounds, salts, and signs of ongoing geological exchange. Each clue alone is incomplete. Together they create a world that can be investigated scientifically rather than imagined only in theory. What remains most striking is the discipline of the conclusion. New clues suggest that life on Europa could exist. They do not show that life does exist. They reveal a moon that is chemically richer, more geologically active, and more internally connected than it once seemed. They suggest that its strange ocean may not be sterile by necessity, but may instead possess the ingredients and energy gradients required for biology. The strangeness lies in the setting itself. If life is possible there, it is possible in darkness, under ice, without sunlight, in a sea driven by tides and chemistry rather than by weather and day. That idea reshapes the meaning of where life may arise in the universe. Europa therefore remains both clearer and more mysterious than before. The broad outline is now strong. A bright frozen shell covers a deep salty ocean. Rock lies below. Heat enters from tides and interior processes. Chemistry moves through the system in ways that may sustain habitability. At the same time, the critical unknown remains untouched by direct observation. No one has seen the ocean. No one has sampled its water. No one has measured its biological state. The moon keeps its central secret, even as each new clue narrows the space around it and brings science one step closer to understanding what kind of world lies beneath the ice. In the quiet of that conclusion, Europa settles into view as a distant moon that has become a profound scientific place. It begins as a bright point moving around Jupiter and ends as a layered world of ice, ocean, rock, chemistry, and long uncertainty. Its surface is cold, young, and marked by stress. Its shell appears structured and active. Beneath that shell lies a dark sea, held liquid by internal energy. Below the sea lies stone, where water and heat may meet. Between the irradiated exterior and the rocky floor, gradients of chemistry may persist through immense spans of time. Nothing in this hidden system promises life. Nothing rules it out. The moon offers conditions, not assurances. It offers clues, not conclusions. Yet those clues are enough to change the imagination of habitability. Life need not belong only to warm surfaces under open skies. It may also belong, in principle, to sealed oceans in darkness, where chemistry remains active and patience extends for ages. Europa remains silent beneath its ice. The cracks on the surface do not open fully to view. The ocean does not reveal its contents. The possible plumes rise only briefly, if at all. Still, the evidence now forms a calm and coherent picture of a world that may be alive in the chemical sense, and perhaps more than that. The next missions move toward it not to confirm wonder, but to measure reality more closely. In that careful movement, Europa continues to hold one of the strangest and most credible possibilities in the solar system, that far from the sun, beneath a frozen crust, a dark ocean may have become a place where life could endure.